What is up, everybody? Welcome back, and I'm really excited to talk to you today about a topic in data science called kernel density estimation. This is one of my all-time favorite topics in data science, and let me tell you why. A lot of the topics we cover on this channel are specific tools you would use in specific situations. If your data looks like this or has this property, this is a great tool to use, and of course all of that is really important stuff. But kernel density estimation is something that has proven to be a tool I use on a day-to-day basis in my job as a data scientist. In 90% of the visualizations I create as part of my job, I am using this tool called kernel density estimation. For that reason, it's something I'm really excited to share with you. Now, let's get us started with a cool little example. Let's say you are a fisherman in a local town, and you catch fish and you weigh them. So here's a fish you caught that was 10 pounds, here's a different fish that you caught that was 50 pounds, and let's say you've caught 6 fish so far, and you've logged their weights here. So 9, 12, 10, 55, 62, 50. These are the weights in pounds of these 6 fish you're caught. Now, a question comes to mind. There's obviously way more than 6 fish in this river that you're fishing in. So the question is, can we use just these 6 data points to figure out the population density, the probability density function of weights of all of the fish in the population? And before we really get into how to do this, let's have a little quick discussion on why would you want to do this. Well, this is a very natural extension of a topic in stats and data science called extrapolation, where given some sample, it could be a small sample like 6 or a much larger sample like 6,000, you want to use that sample to make really good predictions, really good estimations about the entire population. For example, you didn't see a fish in here explicitly that weighed 11 pounds, but you can probably say that that's somewhat likely given you saw fish around there that were 9, 10, and 12 pounds, which are really close to 11 pounds. Similarly, you didn't see a fish in here that was 500 pounds, but that doesn't seem too likely based on the sample you have here. So you want to use the samples that you have to come to some kind of estimation about what the probability density function for the entire population might look like, so that you can answer questions like, what's the probability I would catch a 500-pound fish tomorrow? What's the probability I would catch an 11-pound fish tomorrow? And make inferences using that distribution. Now, before we get into the math of it all, let's just take a look at visually what we're looking for with a successful kernel density estimate. The kernel density estimate being this estimate of the probability density function of the statistic, here being the weight of fish for the entire population. Here I have a couple of candidate distributions, a couple of candidate kernel density estimates for this population. Let's see which of them we like and which of them we don't like. So on the x-axis here, I have our actual observations. So here you have the 9-pound fish, the 10-pound fish, and the 12-pound fish. And then on this other region here, you have the 50-pound fish, the 55, and the 62. Now let's take a look at this gray candidate kernel density estimate first. Do we like this one? Well, it does seem to have this kind of bimodality that our data would suggest, that there's this kind of cluster of light fish and heavier fish over here. But what we don't like about it is that it is preserving this local structure. Because we have 3 data points here, it seems like that's leading to the 3 peaks here. And because we have 3 data points here, that seems like that's leading to the 3 peaks here. And that's probably not correct. It seems like if there's 2 modes, they're really this mode and this mode here. But it doesn't really seem to, at least in a fuzzy sense, make sense to have that local noise going on here. And for that reason, we call such a kernel density estimate undersmoothed. Undersmoothed. And as the name would suggest, it just means that this estimate seems like it's not smooth enough. We want something smoother. So let me actually jump down to the very bottom one and look at this orange distribution here. What do we think about this one? Well, it pretty much suffers from the opposite problem. It's kind of generally capturing all of the data, but there are these 2 obvious modes here, at least to me, and this does not capture any of those dynamics. It just says, I'm going to just assume all your data comes from a much wider distribution. I'm going to assume the kernel density estimate here is just this really wide thing. And for that reason, as you might expect, we call such a kernel density estimate oversmoothed. Oversmoothed. Which is basically the opposite problem as before, where we are not preserving any local structures, whereas before we were preserving too many spurious, just random local structures. And you're probably seeing where the story is going, the whole Goldilocks of it all. This green kernel density estimate here seems good. Or just smoothed enough. Because we just got those 2 peaks, but we're not inferring, we're not reading any more into the individual data points. We're just saying that, you know what, there's a peak here. In the middle, I don't expect there to be that many fish who have that weight, and there's another peak here. And then outside of those peaks on the very left, on the very right, again, I don't expect there to be a lot of fish that have those weights. So this hopefully is just giving you kind of a fuzzy sense of what we're looking for with a good kernel density estimate. As we'll see towards the end of this video, this is definitely more of an art than a science, although it is really a marriage of both. But now let's put some math to it all. How do we actually construct these kernel density estimates? So the general idea is actually pretty simple. The general idea is that I have 6 data points, or you might have 600 or 6,000. You have some number of data points. Each data point is going to lend some local density, and this is really the key operating word of this entire concept. If you understand this, everything will be a breeze. Each data point, for example, if I see a 10-pound fish, that gives me some local confidence that there is a good amount of probability density at 10 pounds and in the near vicinity of 10 pounds. For example, if I find a 10-pound fish, that gives me some extra evidence that lends some extra local density to the fact that there could be an 11-pound fish or a 9.5-pound fish. And it gives me less of a probability that there could be something like a 500-pound fish or a 1-pound fish. So the general idea is this very, very simple, very, very intuitive thing that when I see a data point in my sample, that's going to increase my likelihood, increase my evidence or my feeling that there's going to be a higher density at that data point and in the near vicinity of that data point. So now that we've talked about it verbally, let's actually look at it in terms of a picture. And with the verbal and with the picture, that's going to make the math here, which right now looks a little weird, a lot easier to understand. So let's just take a look at these 3 data points that came from our original 6. We had the 9-pound fish, we had the 10-pound fish, and we had the 12-pound fish. Now, let's take a look at them one by one. So with the 9-pound fish, as we said, what we're going to do is we're going to draw a little distribution there. This looks like a normal distribution because it is. Very, very often people use normal distributions for this. And today, let's just assume for the sake of simplicity that we're going to use normal distributions as our kernels or our small beliefs at each data point. And all those words will make more sense in just a second. But given we have found a 9-pound fish in reality, we're going to draw a little normal distribution, which is centered at 9 pounds, but which of course has some standard deviation to give us some confidence that, you know what, around 9 pounds, like 9.5 or 8.5, there's still a pretty good likelihood that we would find a fish there. And this is just visually telling the same story that we were telling here with the intuition, that each data point is going to lend some evidence right where it's centered and also around that. Now, the width of these normal distributions is going to be a very, very important factor, but we're going to get into that towards the later half of the video. So at 9 pounds, we say here's our normal distribution. But of course, we have other data points too. We do the same exact thing at 10 pounds. The only difference is that this one now is centered at 10 pounds, and here, this one here is centered at 12 pounds. And now we do a very, very intuitive thing. Let's say we have a question about what is the probability density, what's your best guess of the probability density of seeing a fish here at 9.5 pounds. Of course, we didn't actually find a 9.5 pound fish, but what we can do is just sum up the probability densities of these 3 fish that we did find, and then divide by 3. In other words, take the average of the probability density estimates for all the fish that we do have here. So you can see here that's going to be the sum of this value, and of course also the one coming from the 12, but that by this point is going to be pretty much negligible. So that's going to put us somewhere around here. If we average those out, we'll get back to about this level. And we can do another exercise. Let's say, what's the probability density function of finding a 14-pound fish over here? That's going to be the sum of these 3 probability density functions, all of which are pretty much 0 by that point. So the probability density around here is pretty much 0. And so basically what we're going to do here, I'm going to try my best to draw this in real time. No guarantees this is going to go very well, but what we're going to do here is we're going to get an averaged probability density. We're going to get an averaged probability density here, okay, for these 3, coming from these 3 distributions. And I definitely could have drawn that better. And my green density here should in reality be lower because it needs to add up to 1, but I drew it above them just so you can get an idea without all the curves interfering too much. Basically what we're doing is we're saying that let's average these three, actually six, because we have more data points on the right, but it's kind of hard to draw all of them. So we're averaging these three probability densities together to get our overall kernel density estimate, our overall probability density estimate for what the probability density would be for all these different values in between that we did not explicitly observe. And that is intuitively and visually the power of this method. Now let's hop over to the math, which is going to be very simple for us because it's basically just matching the picture to the math. So let's say that you're asking about what's the probability density of seeing a 9.5 pound fish. So that would be x here would be equal to 9.5, and this f hat is going to be our estimated probability density function of seeing a fish with that weight. And that's going to be, just like we saw in the picture, the average, which is why you're seeing a 1 over n in the front here, because we're averaging over all the data points we have in our sample. And we're going to sum over all the individual, what are called kernels. So each of these little normal distributions we were drawing around the data points we do have are called kernels, hence the name kernel density estimation, because we're using the density of these kernels to construct an overall density for the entire population. So it's going to be sum over the n kernels, one for each of the data points we have. And here inside the argument, we have x minus x sub I. Why do we have x minus x sub I? X, again, is the point whose density we're concerned about. So here that's going to be 9.5, for example. And x sub I is the data point that we actually did see in our sample. And so by doing this x minus x sub I, that's giving us, for example, if we're looking at the data point 9, centered at the data point 9, what would the probability density be for something at 9.5? And then we're going to iterate over that and eventually get to the data point 12 and also get to the much further data points down here, like the 50-pound fish and the 55-pound fish and so on. And that's going to be asking, centered at the 55-pound fish, what is the probability density of seeing that 9.5-pound fish, which is going to be much, much lower, virtually zero. But it's going to be very positive for the 9-pound fish. So this is basically mathematically telling us the exact same thing we were looking at visually and the exact same thing we understood intuitively, which is that to get our best estimate of what the probability density would be for all of these x values that we didn't even observe in our sample, we're going to be adding up our probability, our likelihood, our confidence of seeing such an x value according to each of the data points we did see. And for data points who are closer to our theoretical data point here, they're going to lend more evidence because they're close to that value. For data points further from that candidate point that we're looking at right now, it's going to be a lot lower because they don't think it's that likely. But the idea is that if there are a lot of points centered around this theoretical data point, this 9.5 pound fish or whatever we are looking at, that's going to lend more and more evidence, which is going to make that even more likely. So hopefully that made sense. Again, the idea is really what's driving everything. The math is just putting into equations this idea. Now there are some open questions, and that's what we'll spend the rest of the video explaining. One is, what is this kernel? I've just been kind of referring to it as this mysterious kernel thing. But this kernel in practice can be any number of different functions. Very, very often it's a Gaussian, and that's what we'll be assuming for the rest of this video because it has very nice mathematical properties. But it doesn't have to be a Gaussian by any means. It can be a uniform distribution, it can be a triangular distribution. You can really use whatever distribution you want here for your kernels. And based on the problem you're trying to solve, other distributions might make more sense in terms of that subject matter domain. But we'll be sticking with the Gaussian kernel today, which just means that at each data point in our sample, we'll be drawing that small Gaussian distribution. So the choice of the kernel is very important, but the even more important thing is this parameter h that I sneakily kind of glanced over in this formula. And that parameter h is called the bandwidth. The bandwidth is going to be determining the width, the narrowness, or the wideness of each of these individual normal distributions that you're using. And if we go back to the previous piece of paper here, that's eventually going to determine whether your overall kernel is undersmoothed, oversmoothed, or a good fit. And that's what we'll spend the rest of the video talking about here is, well, now that we understand the basics of kernel density estimation, how do we actually choose this bandwidth h? How do we know if each of these individual kernels should be very wide if they should be very narrow, or something in between. So to set the stage, again, each of these kernels is a normal distribution centered at each of the data points with standard deviation of h, our bandwidth. And the big question is how to pick h, and it really does matter. Let me put this plot on the screen of different bandwidth values for this data set we've been looking at today of the fish weights. You see that for very small bandwidths, we get exactly this undersmoothed problem, where there's way too many peaks. It doesn't really seem likely that that is the overall probability density of the population. For much larger h's, you see that we get the opposite problem. It's oversmoothed. We're not capturing the local dynamics in our data. But for h's that are in the sweet spot, we are getting a good kernel density estimate. So picking h correctly is probably the most important part of kernel density estimation, even more important than the choice of your kernel itself. So we're going to start by answering this question of how to pick h in a theoretical way. But even more important is going to be at the end of the video, where we talk about the actual practical solutions that people and software use in order to pick the kernel. But first, some theory for you to set the stage. The most popular metric to track whether your kernel density estimate is good or not is called mean integrated squared error, or MISE. You can call it MICE if you want. So MICE is going to be equal to this formula. Again, looks a little bit crazy, but we're going to break it down here. Why don't we go from the inside out? So on the inside, we just have a simple difference. A difference between our estimated probability density for any data point x and the actual probability density at any data point x. We're going to take the difference between those and square them. So that's where the squared error part comes from, so we understand that so far. Now the integrated part comes from this integral here. What is this integral over? This integral is over all possible values of x. So going back to our actual example, that would be going through all possible weights of fish from negative infinity to positive infinity. So we would be saying, what's our estimate of seeing a 9.5 pound fish? What's the probability density estimate versus what's the actual probability density from the actual population of seeing a 9.5 pound fish? We would do the same thing for a 9.6 pound fish and all the real values in between, all across the entire number line. So this integral is basically summing up all of these squared differences for all possible values of x. And what's going on the very outside? This is the mean part. So this is the mean part. And that is an expected value, or an average over all possible samples. Because we took a sample of 6 fish, which were assumed to be independent draws from the overall population. Now we could have gotten those 6 numbers that we saw, and if we did this experiment again, we would get a different set of 6 weights. If we did the experiment again, we would get yet another set of 6 weights. So this expected value is iterating over all possible samples we could have gotten, instead of just a specific sample that we happen to get. So in a nutshell, what MICE is capturing is the expected overall error by using a kernel density estimator of bandwidth h, and how that gives us an estimate of the overall probability density that is close or far from the actual density, the actual probability density of the whole population. Now let's say we were able to calculate this. Now we would just fall back on our typical trick in data science. Anytime we have an error metric where we take the derivative of that error metric subject to the thing that we're trying to figure out, which in this case is the bandwidth h. So we take the partial derivative of MICE with respect to h, set it equal to 0, solve for h, and boom, you have your ideal bandwidth. But as many of you probably have figured out by now, there is a gigantic gaping hole in this whole formulation, which is that to understand the ideal bandwidth h, and to use this formula to do it, you'll notice one of the terms in this formula is the actual population density f. So to understand the ideal bandwidth, we need to understand the true density. But if we understood the true density, why would we be going through this entire kernel density estimation thing in the first place? So it all kind of falls apart there. You cannot use this loss function in any meaningful way by itself, because if you were able to, you wouldn't need to go through this process in the first place. But the reason this formulation is still helpful is because it is the bedrock of a lot of more numerical methods that people have developed, and those are the methods we're going to go through now to close out the video. So there's a couple of different families of methods people have used and implemented in software in order to figure out the ideal bandwidth and still get around this issue of not having to know the true density in the process of doing so. One of the most popular ones are called rules of thumb. Rules of thumb are probably the easiest to implement because they're just some fixed formula that gives you the h, the bandwidth, which is usually a function of the standard deviation of the samples that you actually did collect. So its pro is that it's very easy. You can just plug in stuff about your data and get some estimate for h. The con is that it's very strict. It's only going to give you a good estimate of your bandwidth if your data is assumed to come from a normal distribution. And I'd say most of the time when you're using a kernel density estimate, your data is not coming from a normal distribution. It might be multimodal, it might be a beta distribution, it could be all sorts of different things. So this rules of thumb is only going to get you so far. These next two give a more generalized good performance for distributions of different shapes. This strategy is called the plugin selector. The plugin selector works like this. It says that if I knew certain properties about your underlying distribution f for the entire population, if I knew those properties, then I'd be able to plug in those properties into a formula that is going to give me the ideal bandwidth h. Now, of course, it seems at first like we run into the same issue. How can I know those properties about my global distribution if the whole point of this is estimating that global distribution? Well, this kind of proceeds in an iterative manner. It says that let me use my sample of 6 data points or 600 or 6,000 data points, however many you have, in order to come up with estimates of those properties of my underlying distribution. Now I can use those estimates and plug them into the formula to get my ideal bandwidth h. Now given my ideal bandwidth h, I'm going to get an estimate of the overall probability density function, and I can use that estimate to come up with new estimates of the properties of that underlying distribution. So hopefully you start getting a sense that this is an iterative process. There's 2 passes basically, and they go in a cycle. The first pass is using properties about my data to come up with the ideal bandwidth. Then the next pass is using that estimated bandwidth to come up with more improved properties I know about my data, and I feed that back into a cycle. And the idea is that this is supposed to give us, after a certain number of iterations, a very good bandwidth, a very good estimated bandwidth h. Now the downside here, as you might expect, is that this is a computationally much more expensive process than doing rules of thumb, for example. So it's a bit of a trade-off. We have to do a lot more computation, but ideally get a lot better estimate of our bandwidth h. Another very, very popular strategy, probably even more popular than the plugin selector strategy, is called cross-validation. And the way that goes is this. We're going to iterate over a whole set of different bandwidths h. So we might say h might be 0.1 or 0.2 or 0.3 and so on and so on. And for each of those chosen bandwidths, we are going to calculate the estimated probability density function, the estimated kernel density function here, using all of the data points. And then we're also going to calculate it by leaving one data point out each time. Now the idea is that if we leave a data point out and then recalculate the kernel density estimate, and that causes the estimate to change wildly, then that bandwidth probably was not good because it leads to a huge volatility by just leaving out one data point. A good bandwidth, according to this method, on the other hand, would be one where if we left one data point out, then the overall kernel density estimate would not change all that much. In other words, this is selecting for bandwidths who don't lead to a lot of volatility if our data changes in small ways. And that makes a lot of sense if, again, we flash back to our first page here. Whatever bandwidth h led to this gray kernel density estimate here would not be chosen because, for example, if I left this data point out, then this peak would probably disappear entirely, which would mean that my kernel density estimate changes way too much by just leaving out one data point. And so that's how it's selecting for these more stable bandwidths. And that's why this is probably the most popular method. Cross-validation. Again, it suffers from the same problem as plugin selectors where it's computationally expensive, but it's usually worth it. And the last method, as silly as it might sound, is just doing visual inspection. For example, if I just iterated over a bunch of different h's, as we did in that plot we were just looking at, and I were to get a gray estimate like this, an orange estimate like this, I would kind of just look at those and say, you know what, I don't really have any math in my head to back that up, but based on my 6 data points, those just don't feel right to me, they don't pass my gut check. This green one does pass my gut check, and that's the one I'm going to go with. So as silly as it might sound, visual inspection is one of the most powerful tools at your disposal. In fact, a lot of folks will narrow down the set of h's using these 3 methods here, and then kind of search around that space and do a visual gut check of which one seems like it fits the data the best. But all this discussion is just to say that the selection of the bandwidth H is very, very important, but it's also more of an art than a science. There's not like one strategy that's going to pick you the ideal bandwidth. It's more of an art than a science. So that's all I have to say on kernel density estimation. Hopefully you understand it a lot better than you did when you came into this video. Again, it's something I use all the time in my job as a data scientist because when you're drawing these distributions, it really helps to get a sense of not just what is the histogram of points I did see in my sample, but what is the overall shape of the probability density function for all of the points that could have existed in my sample. And that makes it this amazing tool. So thanks so much for sticking around till the end. Like and subscribe for more videos just like this, and I'll see all you wonderful, wonderful people next time.